Hey everybody, this video is meant to help us out with our next review activity that we're going to do here today. Um, this one is solving quadratic equations by completing the square again, but this time we aren't going to be using diagrams. So if you recall from last week, we learned how to use diagrams to complete the square. Then we started solving equations by completing the square, but we were still using those diagrams. But you might have noticed how tedious and how much of a hassle it became when we had lots of rectangles and squares and different shapes to work with. Well, let's try to get away from that now. So here we're going to solve this equation by completing the square. I'm going to start off by using a diagram just so we can start to understand what we could do with this equation without using the diagram. So I have this x squared piece, these 6x's, and then this 5 right here. So I'll turn a few of them on their side and start to form that rectangle or that square again. Perfect square. Piece these three up here. Again, it doesn't have to be exactly perfect. It's just a diagram to help us. And it ends up looking like this. Would then piece all of these little squares in. And we've got this so far. All right, so essentially what we just did, when we took these rectangles right here and we turned these on their side, we have now split them into two sections. We have one section of the 6 up here and then one section of the 6 right here. The math that we did there was division. We divided the 6 into two different sections, 3 over here and 3 over here. So when we look at our equation, what we have to do is look at this term right here. This term is technically called b. If we were to think of a general quadratic, it's ax squared plus bx plus c. So we're looking at this term, it's called b. I'm not going to leave this here right now though. And we're taking that term b and we're dividing it by 2. So 6 divided by 2, which we can see over there is 3. Broke it into 3. All right, and then we need to think of something else. So when we look back at the diagram, this whole section, if we were to have a completed square here, like if I were to add those extra missing ones, let's make them red. There will be 4 of them, it looks like. One here, and then 3 down here. The number of squares here to complete the square would be 9. That seems like we're taking this number 3 from right here. We had 3 right here. And we're just squaring it. So this area right here is 3 squared. So then over here we'll have, I'll write it right here, we take this number 3 and we square it. And that gives us 9. The reason this works is because now we can complete the square with this number. A perfect square would be x squared plus 6x plus this 9 that we have right here. This is a perfect square. We can see it right here. It's this perfect square if we counted those red squares. The only thing is we've now changed the equation, so we have to think, how do we get back to the original equation? Well, we technically have 4 squares that aren't really there, so we're subtracting 4. And this makes sense because 9 minus 4 gets us back to 5. So we really now haven't changed the equation. These equations are the same thing. And this is still equal to 0. All right, and what's again really cool is that this section right here is a perfect square. It's this perfect square. You know, this length is x, this this little length is x. So this perfect square is just x plus 3 squared to get this whole area. So this is x plus 3 squared. And this is awesome because now we have this quantity squared and we can solve using a quantity squared. Those are easy to work with. Wasn't so easy to work with, expanded out into this form as a sum of all of its pieces. So now our equation is x plus 3 quantity squared minus 4 is equal to 0. And then we can just do the simple math that we've learned in the past. We can add 4 to each side. We'll have x plus 3 squared. Still have this minus 4. And well, let's just add 4 to this side as well. That's still equal to 0. And let's just add 4 on the right side of the equation as well. So we have x plus 3 squared minus 4 plus 4. This is 0. So all that's left on this side is x plus 3 squared. And 0 plus 4 is obviously 4. Okay, our next step, we want to undo the square here. So to cancel out a square, we know all we have to do is take the square root. So we'll take the square root of both sides of the equation. We'll have x plus 3 in here. Which was squared. It's equal to the square root of 4. But remember, there's not just one square root, there are 2 square roots. So this should be or the negative square root of 4 as well. All right, square root of x plus 3 squared is just x plus 3. And that's going to be equal to the square root of 4, which is 2. Or x plus 3 would be equal to the negative square root of 4, which is negative 2. All right, so it should now make sense that x should be equal to negative 1 here, because negative 1 plus 3 is 2. Or x plus 3 would be equal to negative 2 when x is negative 5, because negative 5 plus 3 is negative 2. And we have our two solutions. If you wanted, you can check them by plugging them back into the original equation, but you don't necessarily have to. And that's our strategy there. So again, to complete the square, we don't have to make the diagram. We can just divide this term by 2 and then square it. So this is basically the middle term with the x divided by 2 and then squared. And that's what we'll have to complete the square. And you just got to think, what do I do to get backwards? All right, so you can give this a shot. Some of these will start to get really difficult to use diagrams with because you'll have to make a lot of shapes. So I don't recommend using diagrams anymore. You can start to use this strategy. Hope this helps. I'll see you all on Thursday.